Alright, hello, my name is Matthew Keene, and this is my lab report on Lab 4, oscillations. So the purpose of this experiment was to analyze the motion of a spring mass system where the mass was swinging in an arc while simultaneously oscillating on the spring. I have two of many equations that I use during this lab, the first of which is the velocity update formula, the second of which is Newton's second law, where you take the derivative of momentum with respect to time. We also used principles like the energy principle, where the change in total energy is equal to the change in kinetic energy plus the change in potential energy. And the results of this were that despite the changes in kinetic and potential energy, total energy of a system will remain constant if a system is considered closed. So for the setup, we had to put the mass of the ball so that the oscillation was better representative of what was going on in the actual experiment, and we also had to calculate the initial velocity using the initial position, which was given to us through the tracker data. And then there were also some constants that we had to come up with, including the spring constant and the gravitational constant. And so through the code, we were able to determine that there are two different kinds of potential energy acting on the system, one due to gravity and one due to the spring force. The change in kinetic energy is opposite in direction to the sum of the change in gravitational and spring potential energy, and since energy is conserved, the total energy of the system should be equal to 0. So in order to simulate the motion of the spring mass and Earth system, we used these lines of code. So on the bottom left here, I have my calculation for kinetic energy, which is represented by capital K, delta K, which is just the initial kinetic energy subtracted from the final kinetic energy. We have the calculated gravitational potential energy using G and the mass of the ball, as well as the ball's initial Y position. And then again, the delta UG is just the final minus the initial. And then we also have the spring potential energy, which is 1/2 times the K, the spring constant, and that is multiplied by the change in position squared. And all of that should equal the total energy, and then we also calculated the change in total energy. And on the left here, or the right, sorry, I have my initial energies and my gravitational force vector as well as my spring force vector, and when you add those together you should get the total net force. And then we also have the position update formula and the velocity update formula, as well as the spring update formula, where we just change L hat and the magnitude of L hat as the spring mass system moves. And using this data, I was able to edit the conditions of the start code so that my experiment was better reflected, and estimated the values of each kind of energy, and these were plotted to estimate the total changes in energy. So this is my graph. These are the changes in energy based on the tracker data. So you can see that the blue is the change in kinetic energy, the red is the change in the gravitational potential energy, the green is the change in spring potential energy, and the orange is the total energy. I also have my predicted versus real position graphs. So the blue is the computational model, and the red is the data that I extracted from tracker. You can see that I have the Y position time on the left and the X position time on the right. And the results and conclusions of this were that the periods of oscillation, when you compare them, you can see that the Y values are a lot more extreme than the X values, and this is because the spring is being stretched more in the Y direction than the X direction, and you can see that in the amplitudes. And there is a little bit of error. You can see that my the amplitudes of my graphs are not exactly the same, and that's probably because I'm bad at clicking in tracker, but also because the system isn't actually closed, so the energy is lost to the surroundings in the form of heat due to air resistance. And yeah, that's it. Thank you.